Okay, lesson 6, fundamental theorem of calculus and definite integrals. So lesson 5 was our indefinite integrals. Plus c, plus c, plus c, plus c, plus c. Okay, now, here we're going to be talking about definite integrals. Our boundaries are going to be back. There's going to be numbers in place of a and b. And when that happens, you won't put a plus c because you'll have numbers to plug in. Okay, and we'll talk about exactly how that works as we go through this. Okay, so we've now seen 2 major branches of calculus. Differential, that's our derivatives, that's the slope of the tangent line. Been there, done that like 3 or 4 units first semester. We're working on integrals, okay, area problems. Leibniz and Newton independently discovered a connection between these 2 branches, stated informally that differentiation and indefinite integration are inverse operations. So derivatives and integrals. In an earlier lesson, we used the fundamental theorem of calculus part 1 to define new functions, represent accumulation functions, and provide information about the antiderivative. So that's when we were doing the derivative of the integral, and we talked about how derivative and integral cancel each other out. Okay? So now that's right here. Okay, fundamental theorem of calculus part 1 that we already talked about. If f is continuous on the interval a to b, then g is the integral from a to x of f of t dt is continuous on the interval a to b, and it's differentiable on a to b, and g prime of x is equal to f of x. So that's what we were doing last lesson or so. Alternate notation can be seen by taking the derivative of both sides. I don't remember if I talked about that or not, but what we did kind of talk about is what's happening right here. The derivative and the antiderivative sign are going to cancel each other out, aren't they? Okay? And so that's kind of the idea of the part 1 there. So in words, fundamental theorem of part 1 says that if we define a function as the definite integral of another function, f, then the new function is an antiderivative. We want to turn our attention to fundamental theorem of calculus part 2. Which is basically our evaluating tool. How do we evaluate an integral? Which will give us a tool for computing definite integrals in a quick and efficient manner. Given that f represents the rate at which the function is changing, that is, f of x equals f prime of x, we know that the integral represents the total net change in f on the interval a to b. Okay, so when we talk total net change, kind of like when we talked about area being integral, total net change falls into that category also. So, given that f represents the rate at which the function is changing, we'll talk about total net change. Now, fundamental theorem of calculus, part 2. I'll be honest, I never remember which one's part 1 and which one's part 2. I just know both, okay? But part 2, if a function f is continuous on the closed interval a to b, and capital F of x is the antiderivative of little f on the interval a to b, then, okay, the integral from a to b of f of x dx is equal to f of b minus f of a. And so what this is saying is the antiderivative of little f is big F. So when we take that antiderivative, we get big F. That's saying that we're going to evaluate it and do f of b, the upper limit, minus f of a, the lower limit. So basically, this fundamental theorem of calculus part 2, you'll find your antiderivative. You'll plug in upper limit minus plug in lower limit. And that will be how we will plug our bounds in and actually evaluate it. Okay? I also have it written like this. The antiderivative of g prime of x is g, and again, plug in b minus a. So, down there at the bottom, mine is kind of in words. The definite integral is equal to the net change or displacement. There's another good word. Net change, displacement, in the antiderivative of f over the same interval, commonly known as evaluation theorem. I don't know that I hear evaluation theorem very often, but that's all right. Yes?
So why does little f have big F, but g prime has g?
I wish they would be consistent. So
Right here.
Yeah.
So because this is defining two different functions. And if you look, so in this rule, or in this definition, okay, it all comes down to how it's defined. In this one, it's if function little f, then big F is a antiderivative of little f. Okay, so that's how it's defined. With this, because here's the deal, this is little f. An antiderivative, we don't have a notation like G prime or something for antiderivative. The notation for antiderivative is just to use the capital version of it. Okay, whereas here, they're starting with G prime. And so when you do the antiderivative of G prime, you're undoing the derivative. And so then you're just at regular G. It's a difference here that they use G prime in the integral. Whereas here, when you use F, I need a way to show that it's an antiderivative. And so that's when they use the capital F to show the antiderivative of little f. It's all the difference of no derivative marking here on F. This one has a derivative. So the antiderivative of a derivative takes you back to the original function.
So basically, the antiderivative of f prime would be little f.
Yeah. Yeah, if this had an f prime here, then yes, these would be little f's.
Oh.
But it doesn't, so it's not. Okay? Okay, let's do some math. Our goal will be to resist the calculators. You're going to love it. So, okay, when applying fundamental theorem of calculus, we will follow this notation. Okay, so what's usually done is you take the antiderivative, okay, capital F of x, and then we put a bar, which means evaluate, and we're going to evaluate it from A to B. Then we'll go and plug in B into it, minus, and we'll plug in A into it. Okay? Now, in all honesty, you just need me to do an example for that to make sense, right? Because I can tell some of you are just like, huh? What are you saying, Mrs. Sargent? Find the value of the definite integrals by using the come on, move. Evaluation theorem. Sorry. Okay. So, ignore the 1 and 2 right now. It doesn't matter. Antiderivative of x squared minus 3.
1/3 x minus 3x. 3x.
This goes back to yesterday. This would be where it would have been beneficial to see the notes before you came back. Okay, the antiderivative of x squared. Add 1 to the power, which makes it x cubed, and divide by that new power. So dividing by 3, I'm not going to leave it like this. You could say divide by 3, or what we tend to say is 1/3. And in all honesty, it's probably just because you have me as a teacher. I think probably more than less put the over 3. Okay? Minus, what's the antiderivative of 3? 3x. You're just adding the x to it. Now, if this was yesterday, what would I add on right now?
C.
Plus c. But it's not yesterday. Okay?
She went one thing.
Now, today we have bounds.
Evaluate.
So I'm going to say evaluated from 1 to 2. That is your proper notation.
all you have to do?
Well, we have to actually plug in the numbers.
Dang
Now.
it.
Okay? So now,
So close.
that whole f of b minus f of a. Plug in the upper limit minus plug in the lower limit. And I'm going to write it all out. So I'm going to write it as 1/3 times 2 cubed minus 3 times 2. That's plugging in the upper, yes. Minus, parentheses are hugely important, yes. Now I'm plugging in 1. So 1/3 times 1 cubed minus 3 times 1. Clean that math up and you've got your answer. Don't make any mistakes. No pressure. I'm going to do it piece by piece. I know 2 cubed is 8 times 1/3 is going to be 8/3 minus 3 times 2 is 6. Now we can be fancy here, baby. 1 cubed is 1 times 1/3 is 1/3. Do you want me to go ahead and drop the parentheses and just say minus 1/3?
Yeah.
Yeah.
I wouldn't always suggest that, but this one's not bad. Now, officially it's minus 3 times 1, but
Oh.
it's really minus negative 3.1, so or 3
Plus
times
3.
1. So that's really a plus 3. Do we see it?
Yeah.
Now, the other option is to leave the parentheses in, do what's in the parentheses, and then subtract.
7/3 minus 3.
Okay. Okay, options here. You can put your fractions together, your whole numbers together, and then you're going to have to go the fraction route. Because that 8/3 minus 1/3 is 7/3. That's not going into a whole number. Or we can make everything thirds right now. So I could say 8/3 minus 6 is 18/3 minus 1/3 plus 9/3.
Negative 2/3.
And here's the deal.
Well,
You need a way to do this without a calculator. Understood?
No.
yes.
This has to be doable without a calculator. As much as you hate me for saying that right now.
Okay.
Okay? You have to be able to do that without a calculator. And I'm not talking, I don't know if I have any tests coming up that are on calculator. That's not what I'm talking about. I'm talking AP testing here. This is expected. This is basic this is basic math. Okay?
Why is it negative 2/3?
I don't know. I don't know what the answer is. So
Because
8 minus 18 is 10 minus 1 is 9.
what did you guys say the answer was? I wasn't
negative
listening.
2/3.
I did 8 minus 18 is negative 10. Minus 1 is negative 11.
Oh, that's what
Plus 9 is negative 2/3.
I got it. Okay. Never mind.
Are we there?
It's easy. I just can't math.
So this is going to help you on the lesson you missed, Kylie. But you won't be plugging any numbers in. You'll
But
be
it's not gonna
putting
help me when
plus
I take
C's.
the quiz. Like, oh, I know how to do this, but
Okay,
Not anymore.
B. I forgot you have a quiz to make up. Okay.
don't worry, I'll remind you.
You're great.
There's a
reminder.
0 in there. So.
Exactly. And that's why I put the zeros in
My
there.
mom's like, what's wrong with this? I was like, Mom, I just missed a test.
I just missed 3 days of calculus. That's all. Okay. Before we do B, what's probably the best thing to start?
X to 1/3.
Rethink of this as the integral from 1 to 4 of 3x to the 1/2 dx.
That'd be-
It's a square root.
I thought it was a cube root.
That is not a cube root. That is a constant of 3, which, so if I look in my notes here, guys, what I actually did, here's another option,
Just put the
is you could say put the 3 out front and the integral from 1 to 4 of x to the 1/2 dx. Now, do you have to? You don't have to. Okay.
So I feel like I have to.
They make that look
So.
like it's a cube root.
That is not a cube root. That is way too big to be a
I
cube
was
root.
gonna say, it's usually.
It is full size.
So that's just
That's not a story.
we don't.
Okay. Now, if you, couple different options. So if we just think about this 3 out front, we can just leave that 3 out front. Okay? You don't even have to think about it right now. Save it for later. What is the integral, or antiderivative of x to 1/2?
1 x to 3/2.
Yeah.
Over 3/2. So 2/3 x to 3/2.
Okay. So add 1 to the power. 1/2 plus 1 is 3/2. Officially, we first learned as you divide it by 3/2. But dividing by a fraction is ugly. Dividing by 3/2 is the same as multiplying by 2/3. So officially, we just did that. And this is evaluated from 1 to 4. Now, you can use, when you see that, earlier I used an evaluation, just a straight line, yes? The other thing that is also common is to use a bracket, not parenthesis, a bracket. More typical when you have multiple pieces. Here I was just putting it because I had that 3 out front.
Can you have a bracket and a line? Does it hurt? Okay.
Probably not.
Don't wait value with it.
I mean,
Oh well.
okay. Now, you have an option of which way to go here. My recommendation, I can go ahead and plug the 4 in 1, do all this math, and then just multiply my final answer by 3. However, what do you see right here?
You would cancel out those 3.
Yeah.
What is 3 times 2/3?
2.
2. So you can think of this as 2x to the 3/2 evaluated from 1 to 4. Okay? Oh, which is actually, I actually left the 2/3 in my notes. Ugh, what was I thinking? Now, here's another thought, folks. This 2, that's not going to affect anything, is it? You can actually,
Wait. Never. It's cute. Not cute. It's never equal.
okay,
It's in the bottom.
so this 2 is just a constant multiplied by the whole thing. What we can do here is we can do 2 and just leave it out front. We don't have to have it in both parts. And then just worry about doing x to the 3 halves evaluated from 1 to 4. Does that make sense? So we're doing 4 to the 3 halves. That's putting in the upper piece. And then minus 1 to the 3 halves. Without a calculator.
What?
Okay. Now, 4 to the 3 halves, and hopefully you have more room on your paper than I do.
8.
Okay. The 2 in the denominator says square root. The 3 in the power says power. So this is the what? Square root of 4,
2.
2, cubed,
8.
8. So we really have 2 times 8 minus, what's 1 to any power?
1.
1. 2 times 8 minus 1 is?
14.
I'll go with 14. Did you get there somehow or another?
Yes.
I definitely feel like what I did might have been a little more complicated.
And that's possible. There are a lot of different pieces, you know, like we could have left that 3 out front. We could have multiplied everything by 2/3. You can get more
I had the
complicated.
2. I left the 2 in there, which wasn't like super complicated, but then it was like you gotta make sure it's 2.
Yeah.
Never.
Are you good or do you have a question?
No, I'm good.
Are you sure?
Yeah.
Okay. Ask if you have something. That's what I'm going to say.
I just can't power complicated.
Okay. C.
Can we distribute?
Your first step should be to distribute or FOIL this out.
Yeah.
Okay? I'm not going to say you can't. You don't have to. Okay? I'm not going to say it's not doable the other way. But it gets more complicated with the whole having to compensate with the chain rule and everything. Okay?
Yeah, just keep ignoring.
Yeah. So if we FOIL this, or distribute, 2x times 2x is 4x squared. Outsides, 2x times negative 1 is negative 2x. Insides,
Negative 2.
another negative 2x. Negative 2x and negative 2x is minus 4x. Minus 1 times minus 1 is plus 1. Is that going to be a little bit easier to distribute or to integrate? Okay. Integral of 4x squared. Add 1 to the power. It becomes 3. Divide by that new 3. I'm going to say 4/3. Minus. Add 1 to the power. Becomes x squared. Divide by that new power. You divide by 2. 4 divided by 2 is going to be 2. So you have minus 2x squared. Plus the antiderivative of 1 is x. Evaluated from negative 1 to 1. Okay. I'm going to plug in now. I'm plugging 1. 1's an easy number to plug in. 4/3 times 1 cubed is 4/3. Minus 2 times 1 squared is 2. Plus 1. There's my first piece. Then we're going to subtract. I'm going to start the new parentheses. 4/3 times negative 1 cubed. Negative 4/3 minus 2 times negative 1 squared.
Plus 2.
Still minus 2.
Oh, because yeah.
Negative 1 squared is going to be positive 1. So still minus 2. Keep in mind, I still have the minus out front here. I'm not distributing that. And then plus x.
Minus.
So minus 1.
Not just a
This is a situation, you can do these individually if you want and then put them together. So like here, what's minus 2 plus 1? Negative 1. What's 4/3 minus 1?
1/3.
So I'm claiming that whole first parenthesis is 1/3 minus negative 4/3. Minus 2 minus 1 is minus 3.
Negative 7.
What is minus 3 as a fraction?
9 over
This is going to be 9/3, if you will. So negative 4/3 minus 9/3,
13.
negative 13/3. Write out what you need to. One minus negative 13 makes it 14/3.
That was a blast. I love fractions. I love
You
them.
love that I'm encouraging you to go no calculators here, don't you? Okay. Integral from 0 to pi of sine x plus 1.
Negative cosine x plus x.
Are we with them?
Mhm.
The one I have to think about is it negative cosine x? It is, isn't it? Because my brain, this is how my brain works, the derivative of cosine is negative sine. There's no negative there, so that means I need my negative there. Okay. Fun, we got to do trig. Negative cosine of pi plus pi minus negative cosine of 0 plus 0. Cosine of pi
Negative 1.
is negative 1. The negative of negative 1, though, makes it 1 plus pi minus cosine of 0. Cosine of 0 is 1. The negative of that is negative 1 plus 0 is, I'm dropping it.
Trig is
And if you're not using a calculator, that is what the answer you would see. So like this is multiple choice non-calculator, you're going to see that. You're not going to see 5.14 or something, you know, you're going to see 2 plus pi. Okay? Okay,
Everything up with the
that's fun.
not really.
The square root of 2 over x.
Okay, now, food for thought,
What?
We should change this one.
definitely. Can we agree that the square root of 2 over x is square root of 2 divided by square root of x? That's where my brain first is starting. But then, even then, before I do this, square root of 2 is just a constant, yes? Square root of 2. What about square root of x?
X.
X to the negative 1/2 if you pull it out of the denominator, which you're going to have to do to do the antiderivative. Okay. That square root of 2, you can just plop out front for right now.
You don't have to put an X on. No, because it's not needed.
No, it's part of the same term. Okay, so you can just think of it as a constant. We could have put it out front there. Now, x to the negative 1/2, add 1 to the power makes it x to the positive 1/2. Dividing by that new power of 1/2
Times 2.
is multiplying by 2. Oof, I got that too close. Now, the square root of 2 and the 2 are both constants, yes?
Mhm.
I'm just going to think about them out front as 2 square root of 2. I'm going to do x to the 1/2, so it's going to be, what if I say the square root of 8 minus the square root of 1? Or 8 to the 1/2 minus 1 to the 1/2, right? What do you know about the square root of 8?
2 squared. 2.
Are you guys with her?
Yeah.
It's 2 times 4, so it's 2 square root of 2. Minus, do not write square root of 1 for your final answer. The square root of 1 is 1. You could possibly leave it like this if you distribute it.
Got 2.
What is, okay, here's a challenge, 2 square root of 2 times 2 square root of 2?
2.
No. I don't know.
Well,
The square
I'd
root of
probably
2
just leave it.
8.
Oh, wait.
8.
because the square root's cancelled.
Okay, so square root of 2 times square root of 2 is 2. Times this 2 and this 2.
So 2 cubed.
So 2 cubed, which is 8. And if you distribute 2 square root of 2 times minus 1, you end up with 8 minus 2 square root of 2.
I was doing it different way. I was doing square root 2 times square root 2. That's not it. Times 2 instead.
Wow.
Okay,
Nice.
not bad. We got a late start. We got all but one done. We just have a lot left to go, but that's all right. You could probably start looking at some of the homework if you want.